Today, yes, I'm excited to introduce Luca Gómez Bachar. Today, I met Luca a while ago through a collaboration with the University of Buenos Aires when he was a master's student. Luca graduated and is a PhD student in Buenos Aires in collaboration with Harvard with a group of Cora working in physics. And he's going to be telling us today about the work he was doing in his master's, and now he's moved on to a similar but different topic. Still cosmology, still machine learning, but I imagine transfer to flight systems.
CMB.
Oh, CMB, sorry. Yes, okay. So anyway, take it away, Luca.
Well, hello everyone. I have to say this is the first time that I give a talk, and moreover, this is the first time that I give a talk in English. So please do all the questions that you have. And if you don't understand something, please ask me. I have a nightmare last week about someone doing questions and I didn't understanding the questions. Please don't be afraid. I should be afraid, not you. No. Today I will talk about this work, which Cecilia told, and thank you, Cecilia, thank you, Joshua. This was the work for my master thesis, and we continue working on this for some time in the last year. And this is close to be a paper. I mean, it's a journal accepted. We are close to it, so we hope. I will talk about this, which is called Evolution of Linear Matter Perturbations with Error Bundle Physics in 4 Neural Networks. And this is a work that we done with Augusto Chantada, with Susana Landau, Claudia Scopola, and Pablo Protopapa. As Cecilia said, right now I'm working at ITEDA, which is my place of work in Argentina. And this was a job done in the University of Buenos Aires, and I'm in a fellowship with Cora working at Harvard University. Okay, and a spoiler, because when I was practicing the talk, I realized that maybe it was hard to follow. So this is a spoiler to keep in mind. We developed the method to estimate the error bounds applied to the solution of the differential equations using physics in 4 neural networks. Yes, and well, this is an important point. Those are nonlinear differential equations. So this is to keep in mind. And please, if you feel lost, ask all the questions that you want. Well, so today I will start with the motivation, which I found important because I think that these talks, if there is no clear motivation, will be really boring. Then I will give a brief introduction about the physics informed bundle method that we use, and also the equation that we solve. And I will present some results that we get. And I will omit a lot of technical details. So if you are interested in some detail, ask about. But I will try to make the point on the important things and the concrete things to keep in mind. So okay, the motivation to motivate the work, we have to think on why can we trust in numerical solutions. Yes, and I will ask you how many people here took a course of numerical calculus? You raise your hand. Okay. Because when I took my course of numerical calculus, I learned that with an iterative method you can solve differential equations, and you feel powerful, right? Because in the previous courses you learn that the differential equations are hard, and then you learn that with some steps you can solve differential equations, and you feel powerful. And then you realize that there are some codes, like for example CAM for cosmology, which solve extremely complex system of differential equations. And this is amazing. But then when you took the course of numerical calculus, in my particular case, I took the course with mathematicians, and the whole point of the course was in the proofs. And you said, okay, this is something boring. I hate numerical calculus when I took it the first time. And I particularly hate all these proofs. But I think that right now we understand that they are necessary because we can trust in the numerical solutions because we have all these proofs. If you don't have those proofs, we cannot trust in the numerical solutions, right? So this is the motivation of the work because the physics informed neural network method don't have today a general method to estimate or to at least to guarantee that there are some bounds, some error bounds for the solution, right? to finish this kind of motivation, we found that there are some advantage to the physics informed neural network methods respect of the numerical traditional methods, in particular in computational time. But as I said before, there is no general method to generate error bounds. And there are some tries for linear ordinary differential equations or some perturbative nonlinear equations but there is no general method. And in this work, we developed a method to generate error bounds for nonlinear equations, right? So this is the motivation of the work. So first of all, there is an equation about this. I think that this is important. Okay. Well, so right now I will talk briefly about the neural network method that we use to solve the equations, and also a brief introduction of the matter perturbation equation, with again skipping a lot of details. So this is the equation that we want to solve. It's a second order differential equation which depends on the independent variable, which is the scale factor called A, and also a parameter, a cosmological parameter, which is omega matter, right? And for some,
Sorry, yeah. You have to be very loud.
and for some technical details, we have to implement some change of variables, because when you try to solve this equation using the neural networks, this solution is like an exponential, and the neural networks cannot learn it very well. So we implement this change of variables. We pass to this equation, which I write like a system with two equations of first order. And this equation can be solved with the neural networks. I will show some results, but it's important to keep in mind that these two equations are the same, but this equation is nonlinear. This expression of the equation is nonlinear, and this is the equation that we want to solve using the neural network. So to keep in mind, there is an observable that you can build using this solution, and you can also obtain measurements from galaxy catalogs, which is called F sigma 8, and it depends on the solution of our equations. It depends on sigma 8, which is a cosmological parameter, some factor, and then the solution of the differential equations, and it depends also on the solution evaluated today. Right? This is just to keep in mind. Now we are going to move to the physics-informed neural network method that we implement. So this is a very simple neural network. Our input parameters are the independent variable that in the first equation was the scale factor A, but after the change of variables, our independent variable is n, which is the log of A. And then you can feed the neural network with some parameter. Like for example, theta 1 could be omega matter, which was a parameter of the equation. So the neural network will learn to solve the equation as a function of the independent variable and also as a function of the parameters of the equation. And this is the power of the method, because if you then want to explore the parameter space, you have not to solve an equation for each choose of the parameter. You just evaluate the function. And well, the neural network took this and made the calculations and give us a result, which we are going to call yn. And there is also obviously an xn, like we have two equations, y and x are our solutions. We have yn and xn. So the next step to understand how to build the method is impose the initial conditions. Yes. And the neural network has not to learn the initial conditions. We impose it through reparametrization, in which we y naught and x naught are the initial conditions. And if n, or initial value of n is -1, you can see that if n is equal to -1, this term vanishes. So this reparametrization satisfies exactly the initial condition, and then those are the solution of the neural network which we want to learn. Okay. So if we do this reparametrization, we can plug it into the original equation, and we get this, where the difference of the previous slide is we have y tile and x tile, and this is not equal to 0. This is equal to some residuals, which this is if we can make that the residuals goes to 0, we make that the neural network solution goes to the exact solution, right? So our goal is minimizing these residuals And the residuals are very important because our method to generate the error bound, we only use the residuals and the equation. So these residuals are important functions and are they contain the information that we have during the training. So we can build a loss function summing over the batch the residual, the square of the residuals. So if we minimize this quantity, we can train the neural network to solve the equation, and we don't need any numerical solution or anything during the training. So this is the power of this method, that we don't use numerical solutions to train, and well, we don't want to use numerical solutions to bound it. Okay, this is an example to illustrate this. There are 4 relations there, but there are just 2 plots because the neural network solution and the numerical solution are overlapped. And at the right panel, I'm showing the percentage error of the solutions. But to generate this plot, I have to compute the numerical solution and compare it, right? And this is what we don't want to do. Okay, this is the point of the work, is generating those plots without using the numerical solution. Okay? And maybe I don't emphasize why. Maybe yes, but I will emphasize one more time. If we say that our method is faster than the numerical method during an MCMC or an statistical analysis method, but then in any point we have to compute the numerical solution to guarantee that our solution is good, there is no point, okay? Because the method will not be faster, it will be even slower because I have to train the network and then compute the numerical solution to compare the network, yeah? So this is the point of the work, is generating this kind of plots without using the numerical solution. Yeah. Okay, it's okay. It is clear. There is any questions? Okay. So the first result that I will show is the error bounds for the PINN solution, right? The solution of the neural network, which are X and Y. So I have to say that this method, so far it was introduction. This is a new thing on the work, right? So this method is not general at all. It's general for under some assumptions. One important feature of the equation that we need to apply it is that we have a first equation which don't depend on the X variable, right? So the first equation can be solved first, and then we can get X through integration, right? This is a feature of this system. It's important in our development to get this. And it is also important that this first equation forms part of the family of equations, which is called the Cathy equation, which is a nonlinear equation, but it's not anything. Right? The nonlinearity, this term, which has not to be small, so this is not a perturbative approach, but we need these assumptions. So the idea is we define a quantity called eta, which is the difference between the exact solution and the neural network solution, right? And then we expand this quantity eta in an infinite sum of different functions eta y. And we prove, and I will show something, not all the math because it's really boring, but some point important. We prove that you can bound the absolute value of this quantity eta as this quantity that is here. Where this is the bound. This is the important quantity. And the bound has 2 terms. It has this first term, which is a sum of the etas. And you will say, what are these functions? Okay, we can obtain these functions through direct integration. I will show in the next slide some details about this. But you can sum some threshold, this quantity, and then the rest of the sum, this is an infinite sum, and we are not truncating the sum because these etas have not to be, there are no properties of convergence or whatever. Well, it has to converge, but it is not clear how it's converging. Indeed, this set of eta is not unique. Yeah, but this term represents the infinite sum that we can compute it exactly, and all the details are in a previous paper from Augusto. But well, the important thing here is we have this contribution that we can compute some etas. We cannot compute the infinite set of etas for obvious reasons, but we choose a threshold, for example, say y equal to 10, then I use a code to compute the first 10 values of the etas. I compute this sum, and then I have to correct with this term. Yeah. So some details about this. Well, first I will say something. This R, it depends only on the residual of the equation. Okay. So in this expression we have the etas, which depends on the residual of the equation, and depends also of the function in the equation. And then we have this quantity R, which also depends on the residual. So the idea to give a rough approach to how to obtain these things is, suppose that we have an equation like this, right? And we define the etas like in the previous slide. So I just came and replaced y by the solution of the neural network plus eta, right? So my equation becomes this thing. And if I play with this equation and works a lot, you can get until this expression. Yeah. And this expression is an infinite sum of things equal to 0. Obviously, you cannot say that you can take any one of these terms equal to 0 independently, because all those terms are related. But in our case, the etas are not unique, and this is contained in this equation because there is a lot of sets of eta that solve this equation. But we can choose the etas because we don't care the etas. The etas are a way to go to the bound. So in our work, we choose that every one of these terms is equal to 0, and this defines a set of infinite differential equations for eta term to term. Something important, this function S depends on the previous etas. So for example, this equation is not for eta 0. Eta 0 we get through the integration of the residuals. Then for eta 1, I need eta 0. But I can compute it inverting this differential operator. This is something that we can solve with numerical integration, not a numerical integrator, right? This is just an integration. So this is the way to get the etas. And then we can build the etas until the threshold and compute this, because this quantity R, as I said, is just the integral of the residual. And then we have the bound. And again, we are not using a numerical solution, and we are not using any information which is not from the differential equation or the residuals of the neural networks. There is any question here? I mean, this is to be boring, but do you understand the main point of this? That we have this bound, which we can compute it using the residual and the differential equation, right? Well, so schematically, what we are doing is we have the exact solution, which is the black line, and then we have the neural network solution, which is the yellow line. The eta is the exact difference between the two lines, but the bound is a bigger quantity that contains eta, and for the bounding y, we also proved that we can generate this bound. Well, this is the schematic view of this. Then for x, is the same, some of the same. We can repeat the process. Again, I will give some details very briefly, but we can, the main point is we can compute a quantity, which is again a sum until some threshold. And here appears, this is the residual of the second equation, because this one has two sources of error. One source is the neural network solution of the equation for x, which is the second equation, and it appears here. But then, as we are integrating the solution for y, we have the error of y inside this expression, and this appears, for example, the etas are only computed with the information for y, and it appears in the expression for the bound for x. And this term is almost the same. This quantity R is the same as before, so it depends on the residual for y. So we have the bound for the second equation, we have the information of the first equation also. Okay. Well, this is again roughly to define this bound. We have the quantity y, which is the derivative of x respect of the independent variable. This is the definition. And we can define it, well, we know that y is the approximate solution plus the eta. And then we also know that this exact solution, we can write it like this. And then we can get the value of the derivative of eta x in terms of those things. Again, eta x is measuring the difference between the exact solution of x and the neural network solution. And again, we can integrate this. This is a direct integration because we know this, and well, we don't know is exactly that we have a bound for this. So we cannot compute it exactly, but we can prove that if we write eta x like this, we can generate the bound. Yes, and we are generating a bound for the absolute value of this point. Again, we cannot compute exactly the etas, but we can prove that we have a bound that is working, again, using only the information from the training. Okay, so this was so far I talked about the bounds for the solution of the neural networks, and this is those results are well presented in the paper of Augusto. Right now I will discuss how to apply these bounds for the solution of the neural network to the observable, because this is not straightforward. We can discuss it, but so to remember, the expression of our observable in terms of our quantities is this one. And it is not trivial to propagate the error because we tried using error propagation, but the problem with that is you are doing a linear approximation at first order, and then you make an approximation and then you bound it, and this is not rigorous. And when we tried it, we found that the error bound was overestimating the error, which is terrible because all the thing of the work is generating a bound which is not overestimating the error because this bound doesn't work, right? So our best strategy to do it is through the mean value theorem. And here we are basically defining the eta for f sigma 8, which is the difference between the observables, and this is evaluated on the exact solution, and this is evaluated on the neural network solution. And this tile, ignore it, it's just because we divide by sigma 8, which is a parameter. So we know we have this because we have the solution of the neural network, but we don't know this. So the mean value theorem says that exists a point R in a line, in a segment line that have as endpoints this point and this point, which this equality is valid. This is an exact equality. There's any approximation there. And then we have to include the norm of the difference between x and x tile and u and u tile, but those are the etas, right? So we can, right now we can bound it in a rigorous way because we can bound the gradient as the maximum of the gradient in some region that we are going to discuss what is this region right now. And we can bound the etas by the bounds that we found. Okay, so to make a checkpoint right now, we have the expression for eta on the observable that we want to bound related with the maximum value of the gradient in some region and the bound that we found for the physics informed neural network solution. Okay, so far so good. Well, and the next discussion that I will lead is how to build this region, because this is not clear. We don't know this point, right? So to remember I already say that this is the mean value theorem. So this equality holds for some point between a segment that has an endpoint, the points that we are interested, right? So we know one of the points, which is this, we know this, but we don't know this. So in what region are we going to search for the maximum of the gradient? Okay, the safest region that we can choose is, okay, I can take this and expand using the bound, because with the bounds we know that these points has to be included, right? So the procedure to do that is taking the solution of the neural network and going minus the bound plus the bound and doing this for the three quantities. And in this region, we know that the exact solution is, well, we know that the exact solution is in this region, right? And well, what is the problem with that? Well, maybe we are finding a value of the gradient which is bigger than the real value that we can get for a theorem. But this is, well, this could be a problem, but this is not a problem. Right? The bound that we are finding is good and it's working well. Okay, so this is the important point. We can, using the bounds that we developed before, we can make a bound for F sigma 8. And this is, well, this is one of the main points of this work, right? So I will show the last result, which is the computation of this bound, because so far this is rigorous. This is like a math proof, but maybe when we compute the bound, it doesn't work. I mean, this bound could be 1000%, and it's rigorous, but it doesn't work, right? So now I'm going to show the computation of this bound, which is working really good. This plot of the left is the percentage error of the quantity F sigma 8 using the bound. We have 100 times the bound divided by the quantity, yes, that we get using the neural networks. And we found that for, well, this is not a one-dimensional plot because we have the independent variable and we also have the parameter, right? There is no line, but this plot is the analogy of the first line that I show in the example, right? So we found that we have percentage error, which is lower than 0.5% in all the region that we are interested. And at the left and the right, I'm showing a plot, which is the bound minus the difference with the numerical solution. This plot is only for sanity check, because, for example, when we do propagation of errors, we found some points of this plot which was negative. So if there is a point in this plot which is negative, it means that the bound is underestimating the error, and this obviously doesn't work. So this is a sanity check. Well, another conclusion of this plot is, or the error generated by our method is at least is roughly 2 orders of magnitude lower than the error on the data, because the data has an order of roughly 10%. So we can ignore the error during the MCMC. And this is fun because you say, okay, this is a lot of work, and then you ignore the error. So you generate the bounds, but you are not using them. Well, but this is the same that you do with a numerical method, right? When you use a numerical integrator, nobody cares about the error of the method. You get a numerical solution, you say, okay, this is the exact solution. And if you want to compute something, you can, if you want to do a statistical analysis, you will not use the error of this method, but you are sure that you can. Well, now we are sure that we can, even for using this method of the neural networks, and again, not using the numerical solution to check and making the method slower. So as a final comment, I didn't make all the point on this thing because I think that this talk was most interesting in terms of the machine learning stuff. But during the work, we developed a new compilation of data for F sigma 8. This was an amazing job, mainly from Claudia Coppola. And the error of this is, again, you can see that it's roughly of 10%. So this is an error which is bigger than the error of our bound. So again, we ignore the error of the method during the MCMC. And using this new compilation of data, we found a tighter constraint of omega mater and sigma 8 compared with previous work. The previous work, the most recent that we found, was the Nesseris et al. Paper in 2017. Well, using this data compilation, the bounds are the estimation of the parameters is tighter than before. So this data will be available if we get the paper published. So we are waiting for that. And well, as a summary, we developed a method that allows us to estimate the error bounds for the physics-informed neural network. Then we understand how to apply these bounds to the observable that we are interested. We found that our bound is competitive comparing it with the data errors. And using the new data compilation, we found a tighter constraint for some parameters. Okay, so thank you so much.
Okay, thank you so much, Luca. That was great. Any questions? Yeah, there we go.
I was curious how much faster it says compared to the numerical integration.
We'll repeat the question for the Zoom. How much faster is this than the numerical integration?
Okay, this is a very good question. In this problem, there is no, it is not faster. The numerical method is faster, but in the previous work, if you want to integrate a system with nonlinear equations and heavy nonlinear equations, for example, if you consider the modified gravity and you consider the F of R theory, you have 5 nonlinear equations. And in this problem, we found that using the physics in for neural networks, the MCMC is using the numerical method. It took something like 3 days, but using the physics in for neural networks takes like 40 minutes or something like this. So if your problem has important nonlinearities and there are a lot of equations, it could work too. And I am talking only for ordinary differential equations. I don't know how much faster it will be for partial differential equation, which I understand is the best scenario to apply it. Yes.
I have a basic question about neural network. So what is the physics informed part in your neural network?
And the question is, what is the physics informed part in the network?
That's an amazing question because this is the same question that everyone does. I have to say, I really don't know. I think that the name physics informed neural network is related with the definition of the laws in which you are using literally you are using the equations. So I think that this is why we call it physics informed neural networks. You can also include in the laws physics information, like for example, if you have some quantity which is conserved, you can impose in the laws that your solution conserves some quantity. So you can give information. I think that the name is because you are giving the neural network the information using the physical system through the equations. But yeah, in our case, we are not including any conservation law or anything. We are just using the differential equations to build the laws and to train the network.
Another quick question. So did you use the complete CMB data for your final constraints or the first release?
Oh, I'm not using CMB data here. This data comes from large scale structure, but we use the data at the end of using the laws, you train the network, you get the solutions. With the solutions, you build the observable, and this is what we use in the statistical analysis using this new data. But what we use the solution of the neural network to build this quantity. This is our theoretical prediction. And then we compare our theoretical prediction using the neural network solution with the data that we have in the compilation.
Very basic because I already forgot. Can you remind me what X is? And then I'll have the full one probably. The actual physical quantity.
Yes, sorry. X is when you have the system, you start with this. You make the change of variables. X is the logarithm of delta matter. Delta matter is the quantity, the matter perturbations. X is the logarithm of this, and then we define y, which is the derivative of x.
So this is like saying at every time step when you're like solving it, you're passing through the network at different time steps that you're involved in. Is there a regime where it does terribly better than the other, like earlier times or later times?
I think in this problem, I think no, there is no regime like this because when these variables, the equation is the solution are roughly linear solutions between 0 and 1, and are nice solutions. So in this case, no, I think that there is no any regime in which the solution is not worse than the other ones.
And just along that same line, you're minimizing two residuals. How do you ensure proper balance such that one doesn't have the other? And you told us information about both equations.
Can you repeat? Sorry,
You're using two like residuals in your loss. How do you ensure that there's proper balancing, like the actual numerical values and the gradients that are being there, such that these two, both have shared information properly?
I see. This is an amazing question. Well, we compute the residuals and we found that they have the same order of magnitude.
Oh,
But at some point using this change of variables, we have to do a lot of work to find it with previous variables. For example, using this equation, we found that one residual has orders of magnitude bigger than the other one, and we have to correct with some weight. But in these variables, both residuals are roughly this, have roughly the same order of magnitude, so this is not the problem.
Perfect.
So in your bound analysis, does this architecture have like the ability to do partial bounds in the sense that you look at the bounds and say, what's the contribution of y or x to the bounds instead of just the marginalized like bounds?
So yeah, but what's the question?
So what does your architecture have the ability to do that? I don't know, like, or do you just get out the ADAs and so therefore you get the bound out and that's it?
Oh, no, we compute, well, the procedure is we compute the bound using the residuals and the equation. And then if the bound is not good, we don't know how to include it in the analysis.
But you can't break the bound down into various different, like a partial bounds where you essentially you have the bound is with respect to y, for instance.
Well, that was a discussion that we had before to compute the bounds, because if the bound is comparable with the error of the data during the analysis, it is not clear how you have to include it. But in our case, which is order of magnitude, we just ignore it. We say, okay, we compute the bounds, and it's this neural network of over all the parameter spaces has an error which is lower than 0.5%. Our data is roughly 10%. Okay, we don't care about the error of the method, so we don't include the bounds during the statistical analysis. But yeah, this is not trivial.
Yeah, because I was thinking more in terms of just figuring out what's important in your equation, right? And saying like what's driving the bound, right? Because there will be situations where that bound is larger and probably comparable to the observable data, right?
Yeah.
And so it'd be really interesting to figure out what's actually driving uncertainty.
Yeah, and also to add to this, in this method, the bound for x is usually higher than the bound. In general, the bound for y is small, it's very small. But then when you include the bound for x, it is bigger. So if you compute the bound for y, this could be something like, I don't want to say anything, but 0.001% could be, and then the bound for x will be like 2 orders of magnitude bigger. Yeah, but I'm telling this like the bounds that I compute. I'm not sure if this is general for this method. I think that usually the bound for x is bigger because you have included in the bound for x the bound for y, so you have more contributions. And maybe it came from generating first one bound and then the other one. Maybe if you make it at the same time, this could be solved, but it is not trivial how to generate this bound. So yeah.
Any other questions? All right, so I think then you're doing bounds, one bound per variable. Is that what you were?
I guess so, yeah.
So you can separate. So this is good to know how they're driving the overall bound, right? Okay, cool. Okay, no more questions. We can thank Luca again.